Hey everybody, welcome to our first video on organic chemistry. This isn't a unit that I want you to keep an open mind about. I don't want to give you any illusions about what we're doing here. Organic chemistry is a very expansive topic. It's its own course and its own branch of chemistry as a science. So there is no way that we can, in the short time that we have, really give it justice. So in these next few videos, I'm going to take you through some of the very basics of organic chemistry. It may be confusing because we will scratch the surface of a large area, but I want you to hang in there and understand what we're trying to do. I want you to have some basic knowledge of organic chemistry because really this is the chemistry that surrounds you on a daily basis. You are made up of organic chemicals other than water, which most people consider as inorganic. Everything inside of you is organic. All the chemicals that you ingest, the pharmaceuticals and cosmetics that you use on a daily basis, those are all organic, or at least 90% organic with some inorganic additives. So it's really all around you. And throughout the year, a lot of the chemistry in society, chemistry in news, chem stories that I'm going to have to tell you will involve organic chemistry, and it has nothing to do really with the AP test. It's just me trying to get you to appreciate organic chemistry and chemistry in general in your life. I want you to be able to understand jokes like the one you see here. The molecule on the left, help save me, I'm dying. Well, that molecule is a diene. That's pretty straightforward. You're thinking, well, heck, I don't know what a diene is. Well, by the time we finish with this, you'll know that's just going to be two double bonds in an organic compound. And then I think you can get the rest of the joke. And I also want you to recognize compounds like in the picture on the right. That's a very simple, relatively simple, organic compound, and it's one that you interact with almost every day. I'm not going to spoil it and tell you what it is. We'll figure it out by the end of the unit. Well, let's get started with some organic basics. Let's talk about what organic chemistry is. It's just the study of carbon and its compounds. And the reason we have a whole new branch of chemistry about carbon is carbon's ability to make bonds is very unique. Carbon can form not just organic compounds, but it can form inorganic compounds. So you can see in this little diagram in the bottom left, I've given you some of the inorganic forms of carbon just that you probably recognize and you did in pre-AP. We're not talking about organic chemistry when we talk about carbon dioxide, carbon monoxide, carbonate compounds. That would be something like calcium carbonate, magnesium carbonate that you might have seen in pre-AP. Carbon disulfide, cyanides, like you have cyanide salts, those things, they're not organic. Organic compounds are when you put carbon primarily with hydrogen, so that's the backbone of every organic compound, and then you can throw in carbon compounds with other elements such as some oxygens, some nitrogens, some sulfurs, phosphorus here and there. You can put in some metals and much more complex molecules. We'll never get to that in here. But that carbon-hydrogen framework is really what makes organic chemistry. Now here's a bit of a Taylorism to help you with that. This is something I've rationalized. It's sort of true. I don't know to what extent it's true. But inorganic compounds, so this is your CO2s and stuff, these are the carbon compounds when your carbon atom is in its very positive oxidation state. Remember from pre-AP, carbon has 4 valence electrons. It's very small. It has a pretty high electronegativity value of 2.5. So carbon really kind of wants to be negative. But when you put it with oxygen, carbon can be made to a positive oxidation state. Carbon dioxide, carbon is +4. Carbon doesn't really want to be +4, but once it's there with oxygen, it's kind of trapped in that state and it's kind of hard to reverse. So anytime you have an oxidation state of carbon in the plus range, high plus range, +2, +3, +4, maybe even some +1s every once in a while, but those high positive numbers, that's when you're going to have inorganic carbon. All the organic carbons, carbon is sort of the most electronegative element most of the time. And so it'll be around 0, maybe a few negative numbers, and maybe even as far down as -4, like in methane when you're doing the oxidation state. So organic is when carbon is the most electronegative. But you can have oxygens, as I mentioned earlier, in organic compounds. What's going to happen at that point is that you only have a sprinkling of oxygens and a sprinkling of nitrogens and things like that throughout the molecule. So you may have 1 carbon out of 20 or 8. I mean, it doesn't have to be a ridiculous number. That may be slightly positive in terms of its oxidation state, but the rest of them will be primarily, I should say, a lot of your carbons are going to be in that negative range. So that's really what the difference is. It's about oxidation state. Let's talk about some of the bonding we learned in pre-AP and how that applies to organic chemistry. If you'll remember, I told you that there are 5 elements in the periodic table that always have to have an octet, and there's never an exception. Carbon's 1. Just to fill it in, it's going to be nitrogen, oxygen, fluorine, and neon. Those elements will always have 4 pairs of electrons, 8 in their octet. And there will never be an exception to that. So carbon can form single, double, or triple bonds to make that happen. If you remember your hybridization, that's going to be either an sp hybrid if you're a triple bond, sp2 hybrid if you're a double bond, and sp3 if you have all single bonds. And if you take that and remember the geometries that are associated with it, if you're sp hybridized and have a triple bond on one side of the carbon, that means you're going to be linear because you only have 1 more spot left for carbon. It'll be a single bond on the other side. So that's linear. If you go to double bonds, any carbon that has a double bond around it is going to be sp2 hybridized, which corresponds to the trigonal planar geometry. And if you have that sp3, where you have 4 single bonds around it, that's really where the magic of organic chemistry happens and allows carbon to form all these chains, very stable chains, and that would be the tetrahedral geometry in 3 dimensions. Let's talk about the polarity of the carbon-hydrogen bond. It's very important to understand that as you learn organic chemistry. Carbon has a 2.5 electronegativity value. Hydrogen is 2.1. So if you take the delta En, it's only 0.4. It's not perfectly nonpolar, but organic chemists consider that to be a very small difference. So for all practical purposes, due to that small number in addition to the bond length that has something to do with it, the carbon-hydrogen bond is considered to be nonpolar, and organic compounds are typically nonpolar unless they're huge and have to take into consideration dispersion forces effects. And so the polarity then, since we have a largely nonpolar bond over and over again, the only way to make organic molecules polar is if you do something with symmetry. Throw it off, make it long and flexible in terms of its shape, or you can put in substituted groups that would throw off the symmetry or add some electronegative atoms. All right, as we talk about hydrocarbons, this is going to be the class of compounds that we're going to talk about just a little bit. Hydrocarbons are the simplest organic compounds. Ideally, they're just carbon and hydrogen only. This is important for you to know because these are some words you might hear in your everyday life: saturated and unsaturated. You've heard that in the context of saturated fats, unsaturated fats. So if you take hydrocarbons, which are simplest organic molecules, carbon and hydrogen only, mostly, a saturated hydrocarbon just means that you have all single bonds and there's no doubles and triples. So all your carbons are sp3 hybridized, all single bonds. We call organic compounds that are saturated alkanes, and then you can also make ring structures we'll get to in the next video about cycloalkanes. So alkane, that A-N-E is very important, that's saturated. The rest of them are unsaturated. That means there will be at least 1 double or triple bond somewhere in the structure. We call those alkenes, alkynes, and aromatics, and we'll talk about their naming in the next video. Another important thing, and this will be the last part of this introduction video, is talking about isomers. This is similar to resonance structures when we did Lewis structures in pre-AP. Isomers are just different ways to draw organic compounds based on a formula. So first of all, isomers are compounds that have the same formula but different ways to draw them. Okay? The first type, we're going to talk about three types. They can get more complicated, but we're going to keep it pretty simple. Structural isomers. So this is a structural isomer is when you just connect the carbon atoms in different ways. I have some pictures here to show you the ways to do it. This is an alkene. This is a double bond in an organic compound. The one in the top left is called 1-butene. That just tells me where the double bond is and how many, it's just one of them. Okay, now if you compare the picture on the right to butene, you can see that I've just put the double bond in a different place. So that's kind of like your resonance structure in pre-AP. But we put the 2 there to let you know which carbon it's on. Again, I'll go through the naming upcoming. In the bottom row, you can see I've taken the carbons and put them in different arrangements. I put a CH3 group on top of the middle carbon. I made a closed shape that would be an alkane in the middle picture. And then I did a closed shape with the branch coming off in that final picture. So those are all examples of structural isomers, same formula, same mass, just different ways to connect them. Another isomer is a geometric isomer, and this happens when you just arrange the molecules differently in 3-dimensional space. Well, I guess that's not exactly correct. It's on a 3-dimensional axis, but these will actually be flat around these double bonds. We'll get to that. So geometric isomers primarily occur around the double bonds. And we use the prefixes cis and trans to keep this straight. The reason this becomes important is because when you have a double bond, you have a carbon, and that carbon is going to be, of course, double bonded to another carbon, but then it has 2 other connections to make. Look at the picture there where you see the word steric, S-T-E-R-I-C. Steric just has to do with placement in space. Okay, so don't get too hung up on that word. The idea here is that if I have big, bulky group, we call them groups. CH3 is a methyl group, and they're bigger than just an H, just an H atom. So if I have 2 bulky groups on the same side of a double bond, they're close together, and they're going to repel more. And that has a lot of consequences for IMFs. It has a lot of consequences for how these things bond or react, and that's important. Typically, the less steric hindrance you have, or steric repulsion, the more stable the molecule. That goes back to our saturated and unsaturated fats. Saturated fats, well, you've probably heard of trans fats. Trans unsaturated fats, we all know, don't eat them. And the reason is, first of all, fats that are unsaturated with these double bonds are more reactive. Second of all, if they're trans, if you look on the right, that means the groups are on opposite sides of the double bonds. And at first glance, you're like, well, that looks more symmetric. That looks better. Well, it is better chemically because now they can stack more. Their IMFs line up better, and they're able to form solids easier. We don't want solid fats in our body, so trans unsaturated fats are bad. On the other hand, cis fats are going to be more likely to be liquids because they don't stack very well due to these steric repulsions and these the geometries of these. So cis and trans is very important. One more. The last one I find very difficult. Optical isomers are almost exactly the same. Same formula, same weight, they are connected in the same way. To understand optical isomers, you have to think about what's happening in 3 dimensions. The only thing about optical isomers that we call chiral is there's one property that's different, and that's how they interact with plain polarized light, like polarized as in polarized sunglasses. If you're not sure what polarized means, come talk to me and I can fill you in on that. But chiral molecules, if I have like A and B here, A, if I shine polarized light at this thing, will cause the plane of light to rotate one direction, clockwise or counterclockwise, and B would do the opposite. And that's really the only way at all you can tell those 2 molecules apart. And that doesn't sound like much, but biologically that is a huge deal. Your body can actually find A to be perfectly safe, But B, just because it's an optical isomer rotating light in a different way, it will be perfectly toxic to your body, and it could be a mutagen or teratogen or carcinogen. So those are some very important things. So the only thing about these optical isomers is you have to look at it. First of all, carbons that do this have to have 4 different groups attached to it. There can't be any 2 attachments to a carbon that are the same. So if it's a CH2 anything, like CH2Cl2, that can't be chiral because you have 2 H's on it and 2 Cl's in that case. Okay, if it's CHCl3, it can't be chiral because you have 3 chlorines. It has to be something like, for example, CClFBr. You have to have 4 different things attached to the carbon to be chiral. I think in that example I might have left off the H, but CHClBrF would be chiral. And that's about it. They don't superimpose when you find these molecules. And in the picture, if you follow the picture very carefully, the dotted line represents a mirror plane. So it'd be like showing A in a mirror. It kind of flips around. Now, at that point, you can't superimpose it. So follow the arrow there. It shows you how you flip around the molecule so that you can try to line up A and B. And now they don't line up. The green and the blue don't line up anymore. At the beginning, A, the green ball attached to the carbon in A, was pointing into the page or into your screen. That's what the dotted line means. And the blue one was pointing out towards you. And then in the mirror images, they swap. And that makes it now non-superimposable. It's a 3-dimensional effect. We'll have to get better at that. We're not going to do a lot of that, but I just wanted to introduce it to you a little bit because I found it personally to be very difficult when I started organic chemistry. All right, so in the next video, we're going to learn some of the naming systems.